This week we have Yaobin Chen, who is a new member of the EcoPro group. And you got PhD from Fudan University, right?
Yeah.
Okay. And it's going to present something about in general position. Yeah, please.
Yes, thank you for the invitation of Sami. Thanks. And today I will talk about a topic which I finished in my 5-year PhD. It's based on works. There are 2 results, so there are 2 papers, and this work based on with Xizhi Liu, Jiaxin Ye, Jingyu, Zeng, and Wenhao Zhang. And I will talk about the background at first. The initial problem is an open problem now. It's called no 3 in 1 9 problem. This is 100 years ago. Some people ask, is it possible to select 2n points in n times n grid, such that no 3 are in 1 straight line? We know that the straight line here include the row and include the column and include any other straight line. So it's like this is a straight line. It only contains 2 sheets of the grid. And the problem is still open. By Pedro, we know that 2n is best possible. And now for this interval and n equal 58, we know. But for larger n, it's still open. You can maybe use AI to give a counterexample on these problems. And now, why the problem is very difficult is because the grid, the structure is not very symmetric. So we want to consider another symmetric structure called, D-dimensional finite field. We use D to denote the dimension and F be a field. A k-flight of the d-dimensional field is a k-dimensional affine subspace. For example, if d equal 2, if d equals 2, this 2-dimensional field you can imagine is a plane, and then 1 flight is a line, and 2 flight if d equals 3, and 2 flight is a plane, and 1 flight is a line. And then a point set in the d-dimensional finite field is in general position, means there's no d plus 1 points lie on d minus 1 flight. For example, if d equal 2 in 2 dimensions, it means there's no 3 points on same line, because 1 flight is a line. And if the dimension is 3, it means there's no 4 points in the set lie in the same plane. So this is a generalization of the 2-dimension, 3-dimension case. A coplanar case set means there's k points in a k minus 2 flights. Thus, a point set is in general position if it contains no coplanar tuples or coplanar sets. And the following natural question was considered by Eldridge maybe 50 years ago. How large can in general position set in the d-dimensional finite field be? This is the finite field with size q and the d-dimensional of this field. Denote the answer by a signal like independence number. Eldridge give an example which called moment curve. It's like the Van Mon matrix. And by this example, we know that the maximum in general position is at q. And by Penderhole, we know that the upper bound is at most the d times q. So if we fix the dimension d and let the size of finite field goes infinity, we know that the in general position is something like the constant times q.
So can you show? So you said it's not easy, but can you explain it? Why alpha is at most d times q?
Sorry, let me see. So you can.
I think you just partition it.
You can partition the finite field into q plus one disjoint plane. For example, if you have a plane, then you just partition the plane. with disjoint line. So this is perpendicular. And between these two, we don't know the exact bound for the general position set. And we consider a random version of such problems. A random version means if we pick every vertex with probability independently with P, and we get the P random set S, we denote the alpha FQD P to be the maximal size of general position in the random set S. Note that our function is a random variable, so we want to find with high probability what's the value of the maximal in general position set in the random set. And in 2025, 1 year ago, I published a result with Xi Zhiliu, Jia Xinyan, and Ji Zeng. We determine the asymptotically behavior of the function for 2 dimensions. And in this result, we use the expander mixing lemma and for the adjacency matrix of line and points. But today I don't talk about this result at first. And last year, Balogh and Luo also focus on these problems, and they determine the behavior of this function for 3 dimensions. But they also their method couldn't improve the bound for higher dimension. And recently, in fact, the result was finished last year and published this year. We resolved these problems for every dimension. So I will introduce why the behavior of this function is like 3 intervals. The interval, first interval is a line, and the last interval in the middle, the size of in general position set was kept. It's because when the set is very sparse, you can imagine, okay, the P is very small, it's close to 0. And what happens? You can imagine there is no point set coplanar. It means the whole point set is in general position. So the number of the maximal in general position set is just like the number of the set you pick out. So it's P times Q to the D. And when the probability is very close to 1, what happens? You can imagine you almost pick every vertex into your set S. So if you pick the maximal in general position set from the finite field, dimensional finite field, its size is Q. I mean, if you pick the Q is the large in general position set in the dimensional finite field, and you pick every vertex with probability P for the points in the maximal in general position set. So you can get the lower bounds for the maximal in general position set in the random set S is P times Q. And in the middle interval, when we consider such, we call the type problems, random to random problems, we conjecture that in many such problems, the middle interval was determined by the first interval and the second interval, and then the middle was kept. The order is always 1 minus 1 over D, like this. And you can see that the problem is a discrete geometry problems, but we turn these problems to a hypergraph independent problems and use the container lemma. So I will introduce what is hypergraph container lemma at first. Some people here is very familiar with this lemma. So the lemma means if H is a K-graph, is a hypergraph, and you can control the maximal J degree for the hypergraph. The maximal J degree means if you fix J vertex and count how many edges contains this J vertex, and then take the maximum value of this function. So this is maximal J degree. You can control the maximal J degree, then you can obtain a collection of container such that every independent set was contained in some container. At the same time, you can control the number of container and you can control the size of container. So what happens? We can control the number of dependent states by the container lemma. Now, I will show how can we turn the problem of discrete geometry to a hypergraph independent problems. We consider a d+1 uniform hypergraph J on the d-dimensional finite field. The vertex set is just the points, and the edges, the d+1 edges are those coplanar d+1 tuples. So what we want to find? We want to find a
What?
Oh,
Ah.
yeah. We want to find in general position set in the d-dimensional finite fields. So the in general position set is the independent set of the hypergraph. So our problems from the discrete geometry, we want to find a maximal in general position set. Turns to be we want to find the maximal independent set in the hypergraphs J. And to apply the container theorem, we can look the container theorem. We need to guarantee these conditions. We can control the maximum area degree, and at the same time you have many edges. So these edges we have many edges, and we can control the maximum J degree. So we always call such problems balanced supersaturation conjecture. It means if give me x, this is the point set in the d-dimensional finite field, and x is at least q, then we can find a coplanar d+1 set. So you can make this means we can find a collection of edges on the hypergraph J such that the number of edges is very large. This called supersaturation. And at the same time, when we fix J vertex, the number of edges contained this J vertex can be bounded by a function. This is a function, so this means balanced. We have many edges, and at the same time, the graph distributes very balanced. This is a conjecture of Balogh and Luo, and they find that if we can prove such property or lemma, then we can get the behavior of function. So in fact, in our paper, we mostly focus on these problems. And I will show how can we, later I will show how can we obtain the functions upper bounds by the container lemma. This is the method we use container. Suppose we have a collection of container. By container lemma, we have a collection of container. And each container size we can control is smaller than n. And then we let xn denote the number of general position set with size n. So the number of in general position set of size n means the number of independent sets of size n in those containers. So we know that the number of xn is bounded by the container's number times the m subsets of each container. So this is the upper bound of xn. And then we pick every points with probability p independently. So when the expectation goes to 0, by Markov inequality we know that the probability, the maximum independence, the maximum in general position sets larger than m probability is goes to 0. So we know that almost surely the in general position set is at most m. This is the upper bounds comes from the container method. And now we will talk about the balanced supersaturation for the higher dimension. This is what we do in the paper. So the first unknown case is 4 dimension. It means if we can find if for every point set x is at this q in the 4 dimension finite field, there exists a collection of coplanar facets such that, okay, you can find many coplanar facets at first. The number is n to the 5 over q. And when you fix 2 points, for example, when you fix j points, you can control the number of coplanar tuples. The very simple case is if we have the point set x, the size of x is q, and if the number of coplanar facets in x now is n to the 5, and then we sample each of them independently with probability q to 1 over q. What happens? At first, the number of such coplanar facets is at least n to the 5 1 over q. So the first condition satisfied. And secondly, the number of the maximal j degree was controlled. Why? Because when we know j vertex, we can have 5 minus j vertex is unknown, and for this 5 minus j vertex, each vertex has n choice. So we have n to the 5 minus j choice for the remaining tuples. And for each tuples, we pick it with probability q. So we can get that when we fix j points, the maximal j degree is at most this function. So we can prove the theorem in this simple case. Okay. And but for other case, it may be a little difficult. It means you couldn't find enough coplanar facets. So we have a very important lemma called structure vs randomness. Sorry. It means for any point set u, we let fu denote is affine spanned by the minimal flight containing u. For example, if we have these 3 vertex, this is x, y, z. So what is f, x, y, z? This is the line. It means the minimal flight containing x, y, z. But if x, y, z is 3 points not on the same line, so this is x, y, z, f, x, y, z. Now this means the minimal flight containing u. And for any flight, we can let the nf to denote the number of points on the flight f. And we call I flight f is epsilon xj balance if for any proper subflight, the number of points on the subflight is at most epsilon times the number of points on the flight f. So what this meaning? It's a little confused as writing here. It's like, for example, if we have a 2 flight f here, so what is balance meaning? It meaning we have many points, nf points on the 2 flight, and then for each line on the 2 flight, there is at most epsilon times f points. So this means the points on the flight f is very pseudo-random. It's very randomly like, because any subflight contains at most epsilon and f points. And we can miss the condition at first. So our lemma says there is a Ramsey phenomenon for the point set in the D-dimensional finite fields. It's like, okay, you will happen the following 2 cases. Either you can find n to the d plus 1 coplanar d plus 1 sets in X. So this is the simple case. For example, if d equals 4, we can find n to the 5 coplanar 5 sets in X. Or we can find enough many I plus 1 sets such that the flight is balanced. I will draw on the blackboard to state the lemma. So it means, for example, if d equal 4, the first case means there is 1n to the 5 coplanar tuple. What happens, for example, if all the vertex in X are in same line? There are n vertex, then there are n to the 5 coplanar tuples. It's a very structured, so we call this a structure case. The second condition is there exists I. There exists the dimension I, such that there are n to the n plus 1 sets I plus 1 tuple, n to the I plus 1 set I. So what happens to the I? At first, the first property of I is in general position. And the second property is that the flight determined by I is epsilon x j balanced. We can lose the j at first. It means every subflight f prime was in the flight determined by I has epsilon n fi vertex. So this means the flight determined by I is very random-like. So we call the second condition randomness. We will get our functions behavior discussed by case. As we show, the first case was complete by lost page. So we will consider the randomness case. The randomness case. So at first is the randomness case with high density. It means, for example, if the 4 dimension, the dimension is 4, and I equal to j equal 1, I have explained later. It means there are n to the 3 sets, in general position 3 sets, such that the fi is epsilon x 1 balanced. This means at first the number of fi is very large. There are many points on the flight determined by I. And secondly, for each subflight f prime, there are quite small number of vertex points. And we generate our coplanar 5 tuple as follows. First, we pick in general position 3 sets. We have n to the 3 choice because this one. And then we pick points u in the I flight. This means such size I and u is critical coplanar. And I will explain you by the picture. It will be more clear. So we first find 3 points. This is x, y, z. This is the I. This is fi. Because 3 points will determine a plane. And then we know that the line of xy has at the most epsilon n fi points. And the line of xz has epsilon n fi points. This line also has epsilon n fi points. And then we pick a u outside of these 3 lines. U here. How many choices are we? We have at least 3 epsilon and fi choice for the u. So this is n fi ways to choose u. And then we choose remaining points W. This W is not on the plane. We have n choice for the W. We don't know where is the position of W because it doesn't matter. If we have X, Y, Z, U, W, this is coplanar already because X, Y, U, Z is coplanar now. They are on the 4 points on the same plane. So we sample the such coplanar sets with a very specific probability. The specific probability is a little strange. It's n to the q something and over the number of fi. Then we just calculate the maximal degree for each fi. So you will see that on the high level, when we have a good randomness, so we will give a local probability. So this is a local probability, and then we can still have the balanced acceleration. So when we have a structural case, we give the global probability, and then we get the balanced acceleration. You can see the calculation. In expectation, the number of s is at least n to the 5 times 1 over q. Why? Because we have x, y, z has 3 n to the 3 choice, and for the number, the points u, we have n to the fi choice, and for w, for the remaining vertex, we have n choice, and we keep this with the probability. Sorry, the probability is wrong. It is q to the minus 1 over 2. And then we have n times 5 over q over 1 is much larger than n to the 5 over q. So we have the number of s, and then we calculate the maximal j degree by the same way as coplanar 5 sets. The first case, so we can get the balanced acceleration, but the main difficulty is the low density case. What this mean? This meaning, for example, if we have many, this is another case. I will draw a picture. This meaning if there are many lines, you have many lines, x, y, z, w, and each line you have many points. So the points are concentrated on many lines, not on plane. And then our strategy is to reduce the low density case to high density case. We want to find a 5 coplanar tuple in some way, and then give a local probability. And what is surprising is we use the supersaturation lemma for this case, and then give us a structure in the discrete geometry. For example, what gives means if we have many lines, we have n to the square lines. So these lines means there exists we have at first what the balance case give us is we have n to the 2 sets I. We have x, y. The x, y has many points. So how many such x, y we have? We have n to the square. We have n squared such x, y. So if you consider a graph, this is a graph. This is an vertex graph. And then if you x and y is an edge, if they have such line on the in the d-dimensional finite field, and then you have n square edges, so you have at least n to the 4 cycle. And the discrete geometry gives us that most of the 4 cycle is like this. this is a plane. This is x, y, and then this is another plane. This is z. This is w. It's like something like this. This is x, y, and w, and x, y, z. Most of the forces is like this. And so this is what we use the supersaturation lemma here. And now we will generate our 5-planar tuple by something we call the support-in-large substitution. At first, there are many forces like this, x, y, w, z. And then we want to pick a u. We want to pick a vertex points u, not on the x, y, x, w. It's not on the 4 red line. But it's impossible in this case. Why? Because there may be no vertex outside the line. Many vertex are concentrated on the lines. It means the vertex are all on the xy, xw, wz, and yz. So what we want to do next, we want to find new points y prime in the line of dy. And the y prime will replace the original points y. And then we want to find another new points, z prime, to replace the points z. And then what happens? This happens is the u was in the cube determined by x, y prime, w, z prime. And the u is not on any line or any plane determined by the vertex tuple, points tuple of this cube. It means the u is not on the plane of x, y prime, w, and the u is not on the line of x, y prime, x, w, any line. So we keep write the x, y prime, w, z prime, and the u is critical coplanar. And then we find that we can use the original strategy. We give some local property, and then sorry, it's very short. We can give the local probability, and then we can compute the maximal J degree, like the high density case. And finally, we can get the balanced acceleration. So for higher dimension, we just replace the supersaturation by hypergraph supersaturation, and then discuss more case. So it's no new idea. This is all my talk, and thank you for the invitation of Sunny again.
Thank you. Any questions?
Can you go back to the slide of your main user?
Picture.
No, what I mean is
Slide with main theorem.
yeah, slide with main theorem.
Okay, I see.
With the three
Many pages of
three
it.
lessons.
Yep. Next one.
No, this. Yeah, no, before that. Yeah. So in here, what if P is less than Q3 minus D plus D to 1, then it follows the Poisson distribution such that every random set with high probability they forms in the general Poisson itself. What happens if P is much smaller than this?
You mean this interval?
I mean the outside of that interval, if P is much smaller than that interval.
Oh, you mean P is very smaller than
That is
Q times this one?
I cannot assume.
Oh, sorry.
Because of your
P
yeah,
is-
yeah, right.
There's no points in S.
No, I mean there's a gap because plus little 1 and you are
Oh,
So
you mean
something like,
there's a little O1?
yeah, so between the that probability and the Q3 minus D plus Q3 I think in analyzing the
Oh.
random set with the high probability they don't see the general equation.
Yeah, I think it's with hyperprobability it's like P times Q to the D. Here,
So what I wonder is was there it is no result or
And I think there is no little o1 here, right? There's no little o1 here. It's like q to the minus d to q to the minus d plus this, and then there is a little o1. There is a little o1, and there is no little o1. Sorry.
I see.
Yeah.
I have questions. So this is about the problem of finding maximums in general position set, right?
Yeah.
What if? Can you do the problem of partitioning the set into maximum? No, partitioning set into the in general position set, just like a coloring problem, so that number of parts is minimum. Just like,
You mean we want to partition?
yeah. So
Let's see.
if the each color class you want it to be in general position, right? So in general,
Yeah. Yeah.
it'd
I
be
see.
nice if you can actually partition
Oh,
into
it's
almost equal size
Yeah.
in general position sets, so that the number of parts is
Yeah, we didn't consider in this direction before, but yeah, but I think if the graph is very balanced.
so is
I
there
think
some
we-
chance that this is gonna be
Can
number
we?
of points divided by alpha, roughly?
Yeah, I think like this. It's like it because the hypergraph is quite balanced. You see, right?
Yeah.
And we have this condition, and maybe it's like rodent or something. I don't know. Yeah, sorry. Yeah.
It
Your
might
problem
be
is
interesting.
very nice.
It'd be interesting to see. Any other questions? Yeah. All right, if not, let's thank the speaker again.